Hello, everyone, and welcome to today's webinar on teaching mixed models with JMP and JMP Pro. Some of you may be teaching this topic in your courses. Some of you may also be using these techniques in research. It's actually pretty common when you're building models to study effects that factors might have on a response. Ross Matusalem is the presenter today, the academic ambassador. I'm sure you're going to enjoy this and it'll be very informative. Now, there is both a chat window and a Q&A window. If I could ask, if you have a question, put it in the Q&A window, because that's where I'm going to be monitoring the questions and answering along the way. I may periodically stop Ross if that makes more sense for him to answer, but I'm going to try to answer everything as they come in. There's also a chat window. Don't put your questions there. Now, if you wanted to make a general comment so other participants can see, you can put that in the chat. But if you have an actual question, put it in the Q&A. It'll be much easier for me to see it and respond to it. With that, Ross, are you ready to go?
Yep, I'm here. Can you hear me okay, Kevin?
I can. Perfect.
Great. Well, I'll take it away. Everybody, thank you very much for joining us on this lovely Friday to learn about teaching mixed models with JMP and JMP Pro. So our goal today is to just help you build the knowledge of the mixed modeling tools available in both JMP and JMP Pro, as well as our JMP Academic teaching resources in this area, so that you can use JMP effectively to teach mixed models. As usual with our teaching webinars, we're assuming that you have a background in mixed models already, and you're really here to learn specifically about how to use JMP effectively to teach it. So as we dive in, or I should say, before we dive in, I would like to just give you a general idea of the types of things we're going to cover today. So here is a JMP dataset. This will actually be the first in-depth example that we're going to do. This is a simple one-way ANOVA with a blocking variable, and I'll explain the story behind these data in just a moment. But to give you, again, an idea of where we're going today, we're going to talk about how to set up a variety of mixed models using JMP's general purpose regression tool called fit model. So here's a fit model launch dialog that's prepared this simple one-way ANOVA with a blocking variable. And so we'll see, for example, how to specify a random effect. If you look over in my JMP journal file to the left, you'll see that we'll cover a number of different types of models as well. And I really will try to help make clear to you how to set up these models appropriately with any statistical package when fitting something like mixed models or any kind of complex linear model. A lot of it is all about setting the model up correctly up front. I'll also show you how to navigate the reports for these various types of mixed models. For example, how to find information on both the fixed and the random effects in your models. I'll also show you how to use these models to perform inference directly inside the model report. For example, here we have a 3-level fixed effect. And I might just request, let's say at first, a means plot to find out that it looks like one level of this factor is scoring higher than the other two. And in addition to setting up the models, learning how to navigate the reports, I'm going to give you a few teaching tips along the way. For example, if you teach the concept of shrinkage when teaching mixed modeling, I'll show you how to create this plot right here, which is demonstrating shrinkage of the mixed model means in this example that we're about to do towards the overall mean. So we're going to show how to set up the models appropriately, how to use the reports effectively, and a few teaching tips along the way before ending at the very end with pointers to teaching resources that you can use if you're using JMP or JMP Pro to teach mixed models. Now, before getting into that first example that I just hinted at, I first want to review the differences between JMP and JMP Pro for mixed modeling. So all of your mixed models, regardless of whether you're using JMP or JMP Pro, you will build them using the fit model tool right here under the Analyze menu. Now, in standard JMP, you can fit random effects models, so a very large class of models. You may have also heard of these sometimes referred to as random intercept models, but these are the kinds of models that you can use to analyze experiments with a blocking variable or split plot designs or situations where you have clustered observations. Now, in blue and with asterisks below that are other types of mixed models that require JMP Pro to fit. And I should have mentioned at the outset, if you're not familiar, we have two versions of JMP and JMP Pro, where JMP Pro is a superset of capabilities of JMP. It does everything JMP does, plus some more advanced analytics. And so you can see some more advanced mixed models included in JMP Pro. For example, your random coefficient models, or you may have also heard of these referred to as random slope models, or sometimes hierarchical or multi-level models. So these are situations where we're modeling random intercepts and random slopes, and often the correlation between the two. JMP Pro is also capable of R-side modeling. So that is modeling the covariance of residuals. So for example, in repeated measures models, where the residuals might covary or correlate across different time lags, or spatial models, where those residuals might correlate depending on how close they are in space. And then finally, introduced just in the current most recent version of JMP, or JMP Pro, I should say, that's version 17, generalized linear mixed models. So these are mixed models in which we're using a distribution other than the normal distribution to model our response. So we're going to start out actually in standard JMP, doing a simple random effect model, and actually the model that I just hinted at in that introductory example. So let's take a look. I'll bring the data set back up. This is the data set from an experiment testing the breaking strength. In this data set here, it's called pressure, of different types of metal bonds. So you'll see that we have three different types of metal bonds here, just labeled C, I, and N. And we, instead of taking a separate piece of metal for each individual run, of which you can see I have 21 in total, we had 7 different pieces of metal that are called ingots that we broke into 3 pieces each. So for example, ingot 1 was broken into 3 pieces, and then we applied one of the 3 treatments to each piece and then measured the pressure value here. And then same goes for ingot number 2 and so forth. So this is what we would call a completely randomized block design. So the blocks in this case, again, are the 7 ingots that we have. And we have randomly assigned to each block, or each level of each block here, one of our 3 treatments. So let's see how we would actually set this analysis up in JMP. And we're going to start first using fit model in standard JMP. So when I launch fit model, go to analyze fit model here, I'll take pressure and put it into the Y role. And you'll notice that it launches something called the standard least squares personality of JMP. Now the personality menu, if you click on it, will reveal a number of different linear modeling approaches. Standard least squares is selected by default anytime you put a continuous variable like pressure into that Y role. And so you immediately might think, oh, standard least squares, well, that's not what I'm doing when I fit a mixed model. And your intuition could be correct, but in JMP specific terms, the standard least squares personality can handle basic random effects. And so let me show you how. So after putting pressure into the Y role, I'm going to check ingot and bond and put both of them into our model effects list down below. And now critically, if I have a random effect, I'll select that random effect, in this case ingot, go to the attributes, red triangle, and then declare this as a random effect. And you'll know that you've done that when you have this and random specified here. You'll notice up above where we had our personality dropdown before, we now also have method, where we have REML, or restricted maximum likelihood estimation, selected by default, and that's recommended, though EMS is available as well. You'll also notice that by default, unbounded variance components is clicked, so this would allow negative estimates of variance components. which generally we'd like to leave this box checked unless we have a reason not to. But this is the basic setup of your simple ANOVA with a blocking effect. Probably, I mean, if we're teaching mixed models in general, this very well might be kind of the most basic analysis that we're going to start with here. So let's click Run and see what the report looks like. So we have our summary of fit at the top. And if you've used fit model before in the least squares personality, this probably looks familiar to you. So we have R square and adjusted R square, our root mean squared error, and so forth. Now, if we're teaching mixed models, we're probably interested in both the fixed and random effects. So first, if we're looking for our fixed effects, we're going to look under, first, just what's called the parameter estimates. And this is really the fixed effects parameter estimates. So we can see our intercept value of about 72.4. We see the two parameter estimates for bond type C and bond type I. We're using effect coding here by default. So these are deviations from the grand mean. If you want to switch to dummy or what's called sometimes indicator coding, you can request that as well under estimates and then indicator parameterization estimates. I'm just going to leave this as is and show you also then where we can find the information on our random effects. And that's in the variance component estimates section. Or in this case, it's labeled REML variance component estimates. So this first row in this table corresponds to the one random effect we've declared for ingot. Under variance component 11.45 approximately, that's actually the variance component associated with our random effect. To the left of that, the variance ratio of 1.1, that is the ratio of the variance component to residual variance right here. We also, for our variance components, get confidence intervals and a walled test. So here we can see the confidence interval does span 0 and the p-value is greater than 0.05. So we might say that we lack statistical evidence that there's variability being driven by the random selection of ingots that we have in our study here. Though, of course, this I think actually is a good example of where we might not want to trust p-values entirely. And we may have good reasons to believe or based on prior knowledge or experience know that the breaking pressure of the various ingots that we typically test do vary. And so we should leave that term in the model. But anyway, these parameter estimates and the REML variance component estimates are where you're going to find your fixed effect and your random effect details here. Now, if you want to perform inference, when you have categorical variables, at least, the first place to go, I would say, is the effect details section down here. And so if I open it, I have a section for both my fixed and random effect. So here I have the model estimated means for the 3 levels of bond and a red triangle menu here where I can select additional graphs or analyses. So at the outset, I selected the least squares means plot, which showed us that it looks like bond type I is probably a little bit stronger than bond types C or N. I may also choose to conduct the pairwise t-tests on these different treatments. And if I just get down to, and here, let me get off the bottom of the screen. If I get down to this connecting letters report right here, where levels that do not share a letter are statistically significantly different, I can see that it looks like level I is statistically significantly different from both levels N and C that don't differ from one another. And that corresponds pretty nicely to the plot that we have up here. Now, in this effect details section, I mentioned we also have the predicted means of our random effect here. So here are the model predicted means for each ingot. And so that might make you think, okay, well, so then where are the BLUPs? You know, that is the best linear unbiased predictors or the deviations of each level of our random effect from the overall mean. This is a very common concept that's taught in mixed models. And if you're looking for the BLUPs, you're going to find those under the section labeled random effect predictions. And so let's open that up right here. So you'll see, for example, the BLUP for ingot 1 is negative 1.56 approximately. And we also get the standard error, approximated degrees of freedom, t ratio, and p-value for each one as well. Now here, I'm going to pause and actually show you something that I think is good to know in general anytime you're teaching with JMP. And that's that all of the statistical outputs that you're going to get in any of these report windows can actually be saved as JMP data tables so that you can do other things with it. And sometimes this is critical for helping students understand or these concepts or values or contextualize them a little more. So for example, students might understand, okay, well, the model's saying that the overall mean for ingot 1 is estimated to be 70.8 approximately, but what on earth is this value and why does it matter? Well, let's go ahead and just save out this table of blups. So I'm going to right click on it and go to make into data table. Let me clean it up a little bit. I actually don't want any of these columns. I just want the blups. Next, what I'll do is I'll demonstrate to students that the blup plus the intercept is how we get to those predicted model means. So if I pop open our parameter estimates again, you'll remember that the intercept was about 72.4. So I'm going to double click here and just make a new column. And in that column, I'll declare a formula that is the blup plus this intercept value, 72.39528. So now I have the blup plus the intercept in this new column 3. I won't bother relabeling it for now. I am going to set it to fixed decimal places though, just so that it matches our report. And now let's actually compare. Let's see. The values that I just calculated essentially manually to those in the model report, and you'll see that they're identical. So I personally, and I've taught with JMP in the past, I found it quite useful to be able to easily grab these report tables out and start doing simple things with them. For example, in this case, just some simple arithmetic to help provide additional context to help students understand the relationships between the different values that they're seeing. And I think this is just a nice, clean and simple example of that. So that was just a bit of an aside. Now, if you're a JMP user, you may be familiar with our prediction profiler, an interactive tool for exploring models. And if you fit a mixed model in JMP using the least squares personality, the profiler is there. If you go to the red triangle and factor profiling. And so if you're not familiar with the profiler, maybe you're new to JMP, you will get an interactive graph that allows you to change values of the input variables. So for example, I'm changing from bond C to I to N and see what the model's predicted mean and confidence interval around that mean is. Now, in this simple example, this is essentially equivalent to looking at this LS means plot that I created before. But this prediction profiler can be very nice once you have a number of different factors and potentially interactions with those factors to be able to make the model something visual, something that students can actually interact with and explore. And we're not going to have time to get into it, but I did include in the journal, which you all will receive after the webinar, an example of a factorial ANOVA with a blocking effect where the prediction profiler really shines. So this is how to fit the model in standard JMP and navigate the report. So again, I went to Analyze Fit Model. When I put pressure in the Y, I stuck with the standard least squares personality. I added both my fixed and random effects to my model effects down below, and then I used this attributes menu right here to declare my random effect. So now let's actually see how I would fit this same analysis in JMP Pro's mixed model tool. And this is a more general purpose mixed modeling interface that can handle this simple random effect model that we're building, as well as the others that we're going to build today. So sorry, I'm hanging there a little bit, but let's, get to fitting this same model in the mixed model personality. So I'm going to go to Analyze, Fit Model. Again, if I put pressure into the Y role, standard least squares is selected by default, but you'll find if you have JMP Pro, the mixed model personality right here. And this is a personality that is, you can almost think of it as a format of the fit model tool that is built for the custom purpose of fitting a variety of mixed models. Now, in this case, I'll just take our fixed effect bond and add it to the fixed effects list. And now you'll notice I have tabs over here for random effects and repeated structure. I'm just going to click random effects in this case and add ingot as a random effect. And for this simple model, we're done. So when I click run, you'll notice that the report looks a little bit different by default. Again, this is built specifically for mixed modeling as opposed to more general least squares modeling. So at the top, we can see a good example of one way in which this differs kind of fundamentally from fitting the mixed model in standard JMP with these two plots right here. So on the left, we have a standard actual by predicted plot. So the x-axis are the predicted pressure values from the model, and the y-axis are the actual or observed pressure values. And so we can see this is just a one-way ANOVA with 3 levels. And so we only have 3 possible predictions that the model would make. And then we can see where all of the individual values lie with respect to the predictions along that red line. But over on the right, we have a conditional predicted by actual plot. And so the values on the x-axis here are now conditional on which ingot we're talking about. And so the mixed model platform in general, and we'll see another example in a moment, allows you to perform inference based by marginalizing across the levels of your random effect, or actually by conditionalizing on them. And these graphs are just an initial example of that. But let's talk about the rest of the report here. So as before, if we're looking for our fixed effect details, we're just looking for the parameter estimates table. Though because we're now in the mixed model tool, it's more thoroughly labeled as fixed effect parameter estimates. Right above that, we see the random effect covariance parameter estimates, and that's where we find all of our random effect details. You'll notice that both of those tables contain the exact same numeric values as we saw when we fit this model in standard JMP. Let me close a few of these down. If you look under random coefficients, you will find the BLUPs. So these are the same BLUPs that we saw when we fit this using standard JMP. But you'll notice actually by default, all we provide is the BLUPs. For example, we don't have the confidence intervals next to them. If you want that information, just go to the red triangle and choose under model reports, the random effects predictions option. And now we have that same table that we saw by default when we fit this with the standard least squares personality. Now, finally, we can perform, as I mentioned before, marginal or conditional inference. And for the profilers corresponding to those, we can find them under the marginal and conditional inference menus. So for example, if I choose the conditional profiler, I now have something similar to the profiler we saw before, but I have the ability to actually select which ingot we're talking about. And you can see that just shifts the trace here for bond up or down according to the BLUP associated with that particular ingot value. Now, finally, one thing I realized I left it off these little notes that I've created for you for later. If you were to want to perform inference on the fixed effects here, go to the red triangle and go to multiple comparisons here. And so if I go to multiple comparisons, and in this case, select bond and maybe ask for the least squares means plot and the pairwise students t-tests and click OK, we see that same least squares means plot that we saw before. We also have the pairwise t-tests here, and this is just a graphical depiction of those t-tests. So in this case, we have 2 tests that were statistically significant. That is, their confidence intervals do not overlap this diagonal line here. And those are the 2 tests comparing bond type I to the other 2 bond types right there. So to set this model up again, just to recap, we went to fit model. And instead of using standard least squares, if we have JMP Pro, I can choose mixed model. And when I do that, I get this nice tabbed structure up here where I can add my fixed effects here and my random effects here. And then all the basic outputs that you would expect and that you got in standard JMP are provided in the output. But we also have the benefit of having inference done by both conditioning on levels of our random effect and marginalizing over them. Now, I do want to provide one quick tip, and this is something that I remember when I was a student learning mixed models, I found very helpful. And that's with respect to the concept of shrinkage. And we actually saw a quick graph that I had made before demonstrating shrinkage in this simple bond example. So now to provide a little more context, if you remember, the intercept for our mixed model was 72.4. And so I have a dotted line across here at 72.4. I have the mean for each level of ingot from that mixed model here. So that is, again, the intercept plus the BLUP. And now I also have a point for each one that represents the predicted mean if we were to model ingot as a fixed effect. And we can see quite clearly that all of these blue points here, the mixed model means, are being attracted towards this grand mean or the intercept represented by this line. And so this is shrinkage. If you teach mixed models or you've taken a mixed models course, you've probably seen a graph that looks something like this at some point. And so I'd like to show you briefly how you can make this in JMP. So I have the instructions for making it right here. So you can reference those later to maybe apply them to your own example that you want to teach with. I'll give you the basics for how I did this. So I actually started in standard JMP because standard JMP has this nice table right here that provides the predicted means from the mixed model for each ingot. I used that trick that I showed earlier where I can right click and ask to make that into a data table. Here, let's delete the standard error here, and I'm going to change level to ingot for clarity, and I'll change least squares mean to mixed model mean. And now all that's left is to add to this table the means for each ingot if I were to model them as a fixed effect. Now, there are a couple different ways I could do that. If I were to actually create that model, the means would just correspond to the actual observed means in this case. And I could use table summary to do that. But let's just show briefly, and this might actually highlight to students more clearly conceptually what we're talking about with shrinkage. And here's a little trick for you. If you want to relaunch a JMP analysis dialog as it was filled in before, you can just go to redo and relaunch analysis. And so I'm back in the fit model launch dialog. I'm going to remove ingot from my random effects and actually just add it back as a fixed effect. And click run. So now under the effect details, I have this table, which is the means predicted in the fixed effect analysis. Let's just make that into a data table. And now to join these two together, I could use tables join, but I actually am just going to, because it's so simple, copy these values and paste them right here. And let's call these fixed effect mean. And now finally, I'm going to use Graph Builder to build our graph. So if you haven't seen Graph Builder before, it's a drag and drop graphing interface. So I can just take a column and start dragging it onto different axes or other places in the graph to build out my graph here. So I'm going to put ingot on the x-axis. I'm going to take both the mixed model mean and the fixed effect means and put them both on the y-axis. And you can see we're almost there. So we have the points for each of these estimates. Let's make a couple changes. I'm going to right click. I want to make these blue marks a little bigger. I want to turn the fixed effects means into hollow circles. And then I'm going to double click on the axis and just add a quick dotted line at the model intercept. And here we go. There's my shrinkage graph. So once you get comfortable with JMP and you start to learn a little bit of the ins and outs of the interface, you can actually do a lot with these model outputs. And we've seen two examples already to start showing students or demonstrating to students conceptually what some of these values are. And to me, in the classroom, that's incredibly valuable. When you're first encountering this and you're getting hit with walls of numbers and trying to figure out what they all mean, a graph or doing a little extra arithmetic by hand can really go a long way. And you're able to do that with JMP here. So that's the end of the first example. That's definitely the most in-depth because I think as we go along here with, say, for example, random coefficients models or repeated measures, we've already seen the basics of how to navigate these reports. And it's really just all about how to set up the analysis. But before we go into these next examples, Kevin, I'm going to pause and see if we have any questions that we should address before we do.
We do not, Ross. I'm addressing them as you go along.
All right, thanks, Kevin. So let's move right along then. Close down our various reports and tables here. And let's talk now about random coefficients models. And here is an example that we'll use. So this is a data set on achievement in math class, where for 3,691 students, we have measured their math ability at the beginning of the semester, so pre-test score, and then their learning gain throughout the semester. So you can see 0 means no learning gain. That is, they scored the same on the post-test as the pre-test. A positive gain means they've learned quite a bit. A negative gain, like -24 here, means they have not learned much. And crucially, students are clustered by class here. So for example, these 21 students were all in class 1 with the same instructor and the same curriculum. And so if we want to model the effect of pretest on gain, that is, model the relationship between how much a student knew at the beginning of the semester and how much they learned throughout the semester, we need to account for the lack of independence and observations of students in the same classroom. Now, furthermore, in a random coefficients model, we may want to fit separate intercepts, as we would have in a basic random effects model, and separate slopes to each classroom. And so here's a graph that I've put together. I won't show you, for the sake of time, how I did it, to just illustrate the idea a little more clearly. So actually, let me select a smaller number of classes here. So I have 3 different classes selected, and you can see that they span different ranges of the pretest values. And also, each one looks like it would, if we modeled them separately, have a separate intercept and a separate slope.
It's from Liz.
Apologies if you can hear my Google Home talking to me right now. Sorry about that. So this is the type of model that we want to make, one that allows us to model the difference in intercept and slope of each classroom, where a classroom is just a random selection of all possible classes. And in a random coefficients model, we typically model the correlation between those intercepts and slopes as well. So let's see how we would set up this model in JMP Pro. So we're going to use, again, fit model and the mixed model personality. Gain is our Y variable. Pretest is our fixed effect. And now in random effects, we want to declare random intercepts, random slopes, and the correlation between the two. So let me show you how to do that. And I have, for the notes for you all later, it listed out right here. Instead of adding class first, as say a random effect to get the random intercept, what I'm going to do is start with pretest and click add, because ultimately we do want random pretest slope by class. And so to achieve that, I'm then going to select pretest, which is already in my random effects, select class and click this button right here, nest random coefficients. So let's talk about what just happened right here. This first term, you can read it as intercept nested within class. So that is a separate intercept for each class. And here, pretest nested in class. So that is a separate pretest coefficient or pretest slope for each class. And with this and random coefficients set to 1 right here, what this is telling us is that we're going to fit a random coefficients model that involves a correlation between the distributions from which we're drawing those intercepts and those slopes. So let me back up and do that one more time. I know when I first started using JMP, it took me just a moment to kind of wrap my head around how JMP was doing this. So again, I'll start by adding pretest. Then I'll select pretest and class and click nest random coefficients. And so now I have my traditional random coefficients model here. And I'll click run. And now we are looking at the same basic output that we saw before with the simple ANOVA with a blocking factor. So we have our actual by predicted plots. We have our fixed effect parameter estimates. We can see actually here that the slope for pretest, the average slope across all classrooms, is negative. So that is the higher the pretest score a student had, the lower their learning gain is expected to be. And this might seem counterintuitive, but it actually makes sense. If a student knows a whole heck of a lot going into the semester, they have less to learn than somebody who doesn't know that much. And so their learning gain will probably be smaller. If we look up at the random effects covariance parameter estimates up here, so we can see the variance on the intercept, and the variance on the slope distributions. Crucially, we also see the covariance between the two, and this is at negative 0.23 approximately, and it's statistically significant. Now, I remember back in graduate school is when I first encountered this kind of model, and it was, I kind of had an idea about what these terms were doing or what they meant, right? So, okay, different classes have different baselines, and here's the variability among classes that I'm estimating. Sure. What this term meant, at least for me, and perhaps I was a slower learner, but this confused the heck out of me. And I was really wondering, what does it mean for these things to co-vary with one another? And this is where I have another tip for teachers out there. And that is an easy way to try to visualize, at least conceptually, this covariance. And again, we're going to do what we did before by just saving a quick part of this model report as a data table and then making a quick graph. So let's do that. Let's visualize this covariance by just creating a simple scatter plot. If I go to the random coefficients right here, you see we have that nice simple table. So here's the random intercept or BLUP for class 1, and here's its random slope. Or I should again say BLUP, so you would add this to the slope to get the slope for that class. So let's go ahead and save this out. Again, right-click, make into data table. Now I can open up Graph Builder. I'll take intercept and put it on the x-axis, pretest, put it on the y-axis. You'll notice I have two different elements in my graph by default. If you're new to Graph Builder, all of these things at the top here are different elements like points, lines, density, ellipses, bars that I can add to my graph. I'm going to turn off the smoother, which is essentially just a spline model going through the data here. And I'm going to turn on my density ellipse and take class, and I'm going to actually put class into the color role just so each class is colored by a different point to try to highlight that that's what we're representing here. And I'll click done. And so here I have just a simple visual depiction of the correlation between the pretest slope and the intercept. So for example, if I go up here I have class 118, the BLUP for the intercept negative 0.4, and the pretest BLUP 0.1. So that means lower intercept than average, less negative slope, but probably still negative for the pretest score. Whereas down here, we can see a positive BLUP for the intercept and negative for the pretest. So this is a class that had a higher intercept and in general had an even more negative pretest effect here. So again, what we're doing is by virtue of just making a simple graph based on some elements in our report, taking what is a pretty important concept to understand, this covariance parameter right here, and making it something visual and hopefully more accessible. All right, let me get rid of that line there. And so that's how to fit random coefficients models again. And you may be thinking, oh, we didn't explore the results here in too much detail. That's because we've already seen, again, when we go to the red triangle, some of the things that we can find when we're inside the fit mixed tool, for example, your marginal or conditional profilers, or the multiple comparisons dialog for follow-up tests and things like that. And so for the sake of time, really the focus here is more on how to set these different models up and then maybe the specifics in the ways that their reports might differ. So let's leave that example behind now and go to the third example here. And this is an example of repeated measures. So in this example, there's a pharmaceutical company that's measuring the effect of a couple new drugs for treating asthma. So here's the drug column right here. We have A, C, and P. P is for placebo, and A and C are two drugs being tested against the placebo. You can see we have a number of different patients. So here's patient 201. who was in arm A of this study. So what happened is this patient was administered drug A, and then across 8 hours, once per hour, they were measured in this variable here, FEV1. This stands for forced expiratory volume, and just as a measure of how much air this person can exhale or breathe out in a single second here. So let's take a look at these data graphically. So what we're looking for is changes in this FEV1 over time and how they might differ across the 3 drugs. So let's take a look at placebo first. We have one trace for the 24 patients that took the placebo. If I can just dim them a little bit, you'll notice that it looks like the effect is pretty flat. That is, if you take the placebo, your FEV score doesn't really change across the time after taking the drug. If we go to drug C over here, it looks like actually in hour 1, FEV is shifted up a little bit, and then maybe it declines ever so slightly on average. For drug A, it looks like we see that decline as well, but maybe that intercept, or that, I should say, the FEV value at hour number 1 after taking the drug is a little lower than for C. Now, crucially, actually, let me bring that view back up. Each individual patient might be above or below this average line. So for example, right here in group A, this patient actually had a very high FEV at hour 1 and higher than average at hour 2 and hour 3 and so forth. And so if we model FEV as a function of both hour and drug, this person's residual, that is their distance from this average line that I've sketched right here, is always positive. So the residuals within any individual patient are correlated, and that's what we're trying to address here with a repeated measures analysis, the fact that the residuals are correlated. So let's see how we would actually set that one up. So again, we're going to be in JMP Pro in the mixed model personality. So I'll go to Analyze, Fit Model. Let's change personality to mixed model. FEV1 is our response, or our Y variable. Our fixed effects are drug and hour, as we were looking at in that graph. Now I could add these as 2 main effects. I could cross them to create an interaction between the 2. Or in this case, if you're not familiar with the macros options in Fit Model, these allow you to quickly and easily fit standard model types. For example, I could declare full factorial, and it's going to give me the main effect of drug, the main effect of hour, and the interaction between the 2. So we'll leave that as our fixed effects for now. Now we don't have any random effects here, so I'll leave that blank. And instead, I'm going to move over to a new portion of this launch dialog we haven't seen before, and this is for repeated structure. So repeated structures is for our side modeling, where we're modeling some kind of relationship between the residuals in the model. And you can set different covariance structures under this drop-down right here. And so I'll let that linger for just a moment so that you can see the various covariance structures available in JMP Pro here. And then if you briefly look over in the journal I've been using to the left, once you get your hands on this journal, you'll notice right below the note that I have highlighted a little link, and that will take you to the documentation for all of these different covariance structures. But if you teach repeated measures analysis with mixed models, a number of these are probably going to look familiar to you. And then also notice down at the bottom is where we have some spatial covariance structures, which we're not going to see today. So let's say I wanted to fit an AR1 or autoregressive 1 covariance structure to these data. I'll select AR1. In the repeated role, I'm going to place hour, but I also have hour represented as a numeric variable in JMP, shown by this little blue triangle. And AR1, in this case, will expect a numeric variable. If I tried to put hour as a nominal variable with the red bars here, it would actually throw up an informative error and say, please change that to numeric. And now for subject, I'm going to put patient in nested inside drug, which is how you can read that. And that's because in the way that this data are set up, and I think this highlights an important thing about data structure, patient is actually not a unique identifier. And so I can see that here's patient 201 assigned to drug A. And if I scroll down, having selected patient 201 everywhere, you'll see that patient 201 appears here, but is also assigned now to drug C. And so it's the case that we're actually reusing patient identifiers across the different drugs. These are actually different people in this data set. And so in this case, I also have the combination of patient and drug, and that is our true subject level variable here. So let me click run now. And here we have our mixed model report that we've seen before. You'll notice now I don't have my conditional actual by predicted plot here because I don't have random effects in this model. I just have the covariance structure, that autoregressive 1 structure declared. So here I have my fixed effect parameter estimates. There are quite a few here because I have 3 drugs by 8 hours and their interaction. Here's my random effects details right here. So I can see it looks like there is, with that estimate of 0.92, positive correlation between the residuals at adjacent time points here. And so I might, of course, go to, let's say, multiple comparisons here and have a look at the statistically significant interaction, which I failed to mention just a second ago, but you can see right here. And for example, again, I could ask for a least squares means plot. I'm going to create an overlay and take a look at the effect of each drug across time. And so here I can see that drug C does start out doing a little bit better than drug A, but both of those look a lot better in hour 1 than the placebo. And then their effects start to wear off over the course of a number of hours until both are maybe, I mean, numerically a little higher, but statistically probably indistinguishable from that FEV at hour 8. Now, here's one more tip for you teachers out there. And that is, again, related to an important but perhaps somewhat opaque value right here. And this is that estimate of the covariance between the residuals here. And so how can we help students understand that? How can we help them visualize it? There's actually an add-in in JMP that I'd like to point you to that is useful for that, and then also for helping to choose appropriate covariance structures here. It's called the Covariance Diagnostics add-in. If you're not familiar with add-ins, here's a list of add-ins I have installed. They're just things that you can install into your version of JMP to provide it with additional capabilities. Some of them are written by our power users, others written by JMP staff. And so if you click this link when you get the journal, you'll be able to download the add-in I'm about to show you. But this add-in will actually help you visualize the correlations among residuals in a repeated measures model like this. And let me show you how you would do that. So I'm going to go back to Fit Model. Here's another tip for all of you JMP users. Instead of refilling this dialog from scratch, if I click Recall, it will actually go back to the state it was in the last time I launched the tool. So what I'm going to do now actually is change the structure to unstructured. And what unstructured is going to do is model the covariance between every possible pair of time points. So hour 1 and hour 2, hour 1 and hour 3, hour 2 and hour 3, and so forth. So if I do that, I get an independent estimate of each of these covariances. So here's hour 2 versus hour 1, hour 3 versus hour 1, hour 3 versus hour 2, and so forth. And now this isn't in matrix format. You can see because we have things like the confidence intervals, it's not placed in that format. But what I can do now is go to add-ins and run the repeated measures covariance diagnostic add-in. And you'll notice it's added some things to my report here. And crucially, it's added this heat map that represents the correlation among the residuals at different time points. Now, I'm going to make a quick adjustment here because right now, all of these correlations, which are also represented in this matrix up here, are they're pretty high. And the gradient is actually extending all the way from -1 to +1, obscuring any patterns I might see here. But I'm going to right-click on the gradient and go to Gradient. I'm going to delete the minimum, center, and maximum of the gradient, which is going to cause it to just scale according to the observed values. And I'll click OK. And now I can see an interesting pattern. So lower values are yellow and slowly turn to dark purple here. And if I look, let's say, in column number 1, so these are the correlations between residuals between hour 1 all the way through hour 8, we can see a gradual decay that is blue to yellow. Same here at hour 2 and hour 3 and so forth. And so this gradual decay might actually represent for us potentially an AR1 structure, or maybe a Toeplitz structure. So I could use this to choose what type of covariance structure to fit. But more generally, I can use this to actually just show what the correlations between residuals at time points are. So between any adjacent hours, they're very high. So hour 1 and hour 2 is 0.947. Hour 2 and hour 3 is 0.954. Hour 3 and hour 4 is 0.951. But once we start to get longer time lags, for example, all the way down here, hour 1 to hour 7, that correlation is dropped to 0.748. It's still there. It's definitely still real, but it's much smaller than at adjacent time points. And so if we go back to our AR1 model, and again, we're considering this parameter estimate right here, and actually it's a little different now. I must have parameterized this model. I included a baseline measure. That's what it is. But regardless, what this positive value here is capturing is really these high correlations at time step 1 right here. So just another way in which we can visualize some of these concepts to make them more accessible to students. And again, that's through an add-in. The link is in the journal, which you will all receive after the webinar. And that was the repeated measures, covariance and correlation diagnostics. Now I see we have about 9 minutes left. That should be just the right amount of time to very briefly show you generalized linear mixed models in example 4, and then talk about a couple teaching resources. So here we have a situation in which we have blocking variables and a non-normal response. This is a study on the mating between two different types of salamanders. So these are the types of salamanders. We have what are known as rough butt salamanders. You can imagine why they may have gotten that name. And also white-side salamanders. Again, you might imagine why they got that name. And we could take any combination. So for example, of females, so rough butt females, and have them placed in a situation where they may or may not mate with either rough butt or white side males. In fact, for every given salamander here captured in these subject columns, they're paired with 6 possible mates, and then we measure whether or not they mated. So in this particular case, what we have is a mixed model with a non-normal response. So I'm going to go to personality and select generalized linear mixed model. And here are the notes in the journal for you to consult later. I want to assess the effects of male and female population and their interaction. So that is, are rough butt females more likely to mate than rough butt males? Does that depend on which type of male they're paired with? And then I'll put mated into the Y columns row. Now I'm in JMP Pro 17 right now, fitting this model using the generalized linear mixed model personality. And you'll notice I have basic options here for binomial and Poisson distributions. So binomial for a binary outcome here, mated or not mated. Poisson would be for count variables. I just want to point out that JMP Pro 18 is coming out. It's imminent. In a matter of days, actually, it will be released. And generalized linear mixed models in JMP Pro 18 will have more distributions. And unlike 17 here, where all we can do is include random effects, it will also have repeated measures, covariance structures as well. But for now, all I want to do is include, again, these fixed effects that I talked about. And then because different male or female salamander subjects may have different mating baselines, I'm going to include random effects for just the female and male subjects. So I'll click run, and I get a report out that should look pretty familiar at this point. So for example, I have my fixed effects parameter estimates. It looks like the interaction term is statistically significant. I have the variance components for my 2 random effects here. Neither one is statistically significant, though we get a little bit closer for the female subjects than the male subjects. And actually, if I clicked on the wrong red triangle here where it says binomial for our binomial model, I get the basic output that we've seen before. For example, our marginal model inference, or I could pull up the profiler and get an idea of what this interaction effect is all about. So it looks like right here, if we're talking about the rough butt females, their preference between rough butt and white side males is not very large. This line is mostly flat. Now looking at white side females, we actually see quite a bit of difference over here where it looks like they prefer white side males to rough butt males. So this is just a very quick example of GLMMs in JMP Pro. Again, you just launch fit model. You change the personality to generalized linear mixed model. And then the rest proceeds much like it has throughout all the other examples that we've looked at. And just know again that in just a matter of days, JMP Pro 18, I should say, is coming out with more distributions again and repeated covariance structures. Now, finally, with the last couple minutes we have, let me point you to a few teaching resources that you might find valuable when you're teaching mixed models in your course. The first and most important to know about is this book right here, JMP for Mixed Models, written by JMP's very own Ruth Hummel, Elizabeth Clausen, and Russ Wolfinger. So the examples that I took today, save for the generalized linear mixed model example, are actually taken from this book. This book goes through your basic blocking and split plots through more advanced linear mixed models, each with one or more case studies, screenshots from JMP about how to set the models up appropriately, how to interpret the results. It comes with all of the data sets involved. If you're teaching mixed models with JMP, this is an invaluable resource, either for you as a reference or for your students as well. Down here, I have links where you can find the physical book, the digital book, or just download a sample chapter if you want to get an idea of the contents of the book. But just to show you, it's not particularly expensive. Right now on Amazon, you can get a paperback version of this book for $55 US. And I should mention this book, much like this webinar, is very applied. There's, of course, equations demonstrating the forms of all these models, but it tries to stay high level so that if maybe you're teaching mixed models, not to, statistics graduate students, but maybe to, somebody in a science or engineering program, this should be accessible to them. Now, there are some other resources to know about. First, if you're looking for more sample data, there's plenty for mixed models bundled in JMP. If you go to Help and Sample Index right here, there is a mixed model section where you will find a number of different examples, and each one is labeled right here with the type of mixed model that might be appropriate for it. Just click on any one of these links to find them. In fact, this animals example at the top is actually the example that I didn't go through but provided for you just to explore on your own. Example 1A, a factorial ANOVA with a block effect, which you can find right here. Now, many of you, I see a number of familiar names on this webinar. Many of you are probably familiar with our JMP Academic teaching resources. For example, our case studies or our learning library of quick tutorial videos, and you will find a few resources related to mixed modeling there as well. So for example, at the case study library, and here's the link to it, you can also just go to jmp.com/cases. We do have a case study using generalized linear mixed models. It's called Where Have All the Butterflies Gone? So if I scroll down, or I could do Control F to find it quite easily, we'll find it right here. This is a case study in which we use GLMMs and also actually do some forecasting to evaluate butterfly populations and how they might be changing in different geographic regions. And then finally, in the JMP Learning Library, this is our collection of quick tutorial videos and one-page PDF guides, and I'll pop this open. You can also find it by going to jmp.com/learn. You'll notice we do have perhaps a smaller but still quite useful section on mixed models and repeated measures right here. And so if you click on one of these, for example, let's look at the repeated measures analysis mixed model. What you will find is a quick tutorial video. This one is 3.5 minutes long that walks you through, in this case, standard JMP, setting up a basic mixed model and how to navigate the outputs, much as we have done throughout the webinar today. And then also, when you click View Guide, contains a one-page PDF guide, if it would load here, that just summarizes step by step the analysis done in the video. And so you can take this for reference later. So again, this is the JMP Learning Library, jmp.com/learn, where you can find a few different quick tutorials on how to use the JMP tools for mixed models.